Hello everyone, we are test engineering team from VIP Socket and this is Sungwon Hong.
And I'm Raghav Srivats, and we'll be talking about implementing DFT on via the TSMC PDK.
So here's our milestone table for this semester. This shows the three main steps for the project we were working on this semester: the synthesis, scan insertion, and ATPG using the TSMC PDK. Last semester our focus was on the synopsis flow. We completed RTL to gate level synthesis, scan insertion, and ATPG, achieving full fault coverage and confirming that the scan chains worked correctly. This semester, our main goal is the TSMC flow. We've first finished setting up the environment and verified the scan DFT flow on the PWM sub-module before we applied to the top-level design. We were able to synthesize the entire design apart from some minor RTL issues. The immediate next step will be inserting the scan chains and run ATPG at the top level, as well as focus on OCC implementation. So here's the design overview. In this project, we worked on a PWM sub-module as our design under test. The idea was to apply a full DFT flow to a relatively small block to understand how scan insertion, ATPG, and coverage analysis behave in a contained setup. The main objectives were to perform scan insertion using 1 and 2 scan chains, compare their outcomes, generate ATPG patterns, and measure the coverage. Additionally, we wanted to evaluate whether scan compression was necessary given the small number of flip-flops and discuss how OCC still plays a relevant role in this context. Overall, this serves as a hands-on DFT exploration that builds a foundation for scaling to larger and more complex modules later. This slide shows the key part of our DFT script used for inserting 2 scan chains in Fusion Compiler. We defined all the necessary DFT signals using the command setDFT signal. The scan clock and reset declarations specify existing functional ports that the tool should treat as the scan clock and asynchronous reset during the DFT. The clock timing window 45 and 55 defines the scan shift capture window in nanoseconds. Then we assign the 2 scan inputs and 2 output ports, corresponding to the 2 scan chains and the 1 scan enable signal which controls the scan mode. Once signals are defined, we ran the scan synthesis flow with 4 core comments. First one is create test protocol, which sets up the scan connections and defines the test architecture internally. The second one is DFT-DRC, which checks the rule compliance and design readiness for scan insertion. The third one is preview DFT, which generates a report of expected scan structures before actually modifying the NAT list. The final one is insert DFT, which performs the scan stitching and updates the design with scan chains. The flow for a single scan chain is essentially the same, only the scan count value changes. This allows us to easily compare the 1 scan and 2 scan implementations later in the analysis.
So now we come to the ATPG summary. This table of faults confirms that the scan inserted PWM submodule achieved complete test coverage. Out of 13,472 total stuck-at faults that were analyzed, 13,392 were detected directly, while the remaining 80 were classified as undetectable. These undetectable faults are typically tied off or constant nets that we can't toggle by design, so they don't count against overall coverage. More importantly, there are no untestable or undetected faults, as we can see here, which means that every fault that can logically be tested was detected by the tool. This validates that our scan insertion provided complete controllability and observability across all sequential elements. Reaching maximum test coverage demonstrates that the scan chain structure and ATPG were both highly effective. In a larger context, this confirms the integrity of our DFT methodology and that all flip-flops are reachable. The test points are sufficient, and the module is fully test ready for integration at the SoC level. In this experiment, I made this comparison between 1 and 2 scan chains which I inserted in the PWM submodule. So with a single chain, we have the scan length was around 334 flip-flops and 2 chains was 167 per chain. The test coverage stayed identical at 100%, which means that increasing the number of chains at this submodule level didn't affect fault detectability. However, the most visible improvement was in ATPG efficiency. The total number of test patterns decreased slightly from 289 to 282. However, the ATPG CPU time dropped significantly from about 0.65 to 0.16 seconds. That's roughly a 4 times speed up in pattern generation. This outcome illustrates a key DFT trade-off. More scan chains shorten chain length and reduce pattern generation time, but on the other hand, they require extra scan IOs for data in and data out. In larger designs, this translates to more tester channels and routing complexity. And for this PWM, since it's so small, this improvement is not critical. So our entire design has around 18,000 flip-flops, which is a small enough amount that we can achieve full controllability and observability without the need to add compression hardware. Using compression would only make the design more complex and take up extra area and man-hours without a noticeable benefit. Instead, we focused on implementing an OCC or an on-chip clock controller. The OCC lets us switch smoothly between the slow 10 MHz scan clock and the 50 MHz functional clock during testing. It makes sure that the switch between the two clocks happens glitchlessly and helps us perform accurate at-speed tests directly on the chip. Each clock domain has its own OCC, which helps keeps everything synchronized and reliable during scan operations. And this is what we'll be implementing rest of the semester. Thank you.
Thank you.